full arrow, we've got an arrow in three pieces, and we've got an arrow in 2 pieces. And these arrows are actually used for the arrows that strike the hard surfaces. So any arrows that strike the ground, or any arrows that strike the wall, those arrows actually fracture into different parts. Now, also the arrows that strike the ground, they also actually fracture into different parts. But you know, if the ground was not too hard, let's say it was gravel, you'd expect some of the arrows maybe to bounce off the ground, and some of them to actually fracture, and others to maybe stick in the gravel. You know, maybe they make their way through the gravel and they stick into the earth below. In which case we could have made this this setup a little bit more complex to represent that. So let's have a look at our particle flow, which I'll just drag in here just so we can see it a bit more clearly. I'll just resize it down here. I'll turn off the description and the depot, and we'll have a look at exactly what it does. So you can see I've got a cache set up here. I'm displaying only 50% of the arrows just to make you know, the viewport preview a little bit faster. Then we're caching only the arrows in the viewport. We're birthing the arrows from frame 0 to frame 50, and in total we fire 60 arrows. So obviously that could be adjusted to have a lot more arrows. We position the arrows based on the icon, which, as I showed you, if I just move this over here a bit, is down here. You can actually see the icon down here. This is where they all fire from. And then we're using a speed along the icon arrow, and you can see I'm using a speed of 300 with a variation of 40, and obviously that's to give us some variation in the strength that our arrows are fired at. So this is completely, you know, procedural, the arc that they follow. The rotation of the arrow is based on a random rotation, and that's to give an initial rotation value. And then we're using a force of gravity to pull our arrows back down to the ground. As you can see, because of that, they obviously follow this arc here. And I've just tweaked this value basically to ensure that some of the arrows get over the wall, some of them strike the wall, and some of them strike the teapot, and some of them go beyond the teapot. So we've got a nice sort of variation in what's happening here with our arrows. I'm using a shape instance of an arrow. You can see I'm using this static arrow because when they're flying through the air, there's nothing much else which is needed. You just need this single non-animated arrow. And I'm using a rotation of speed space follow. Speed space, and I'm using a spin of speed space follow. And what that does is, if you actually look at the arrows as they fly through the air, you'll notice that they actually do rotate along their axis. And this is something that real arrows do. The fletching on a real arrow is actually designed to make the arrow spin as it flies through the air. And this actually makes the arrow much more accurate. Exactly the same principle is used on bullets. You know, it's called rifling, and it's inside the barrel of the gun to make the bullet spin as it leaves the barrel. And this obviously it acts as a sort of a gyroscope, and it keeps the flight of the arrow or the bullet much more stable. Then we've got collision, and you can see I'm using U-deflector teapot. This is the first deflector here. And then we've got collision hard surface. So we've got 2 different types of collision basically, and we're just handling collision in that way. So when we strike the teapot, the particle is sent off here into soft body collision. You can see we're using shape instance wobbling arrows, and that's actually this, if I just zoom in here, this actually, this group here, which is called wobbling arrows. So it basically uses one of these 3 arrows randomly, using, you know, the usual shape instancing controls. And once it's got its arrow, it then stops the spin. Obviously when the arrow strikes into the surface, we don't want it to keep on rotating. Obviously that would look a little bit bizarre. It would look like the arrow is trying to drill its way into the person. So the spin is just used here to stop it spinning. And then we use a drag force, as I said, and that just basically makes the arrow, because when it collides, as I said, it's used as a collision detection, but it's not used as a bounce. So the arrow doesn't actually bounce off the surface. It's told to continue, but it's actually this drag which actually brings it to a stop, and stops it you know, carrying on through the body. If you adjust the amount of drag, you'll obviously see that the arrow interpenetrates much more strongly. So if we actually play the simulation through here, you can see this green arrow here is actually struck in the body. You can see it's wobbling around, and you can see